Welcome back to the Sleep Lab. What if I told you that astronaut Christina Koch returned from space 0.014 seconds younger than she should be? This isn't science fiction. This is Einstein's time dilation happening right above our heads. Every astronaut traveling at 17,500 miles per hour literally experiences time slower than us on Earth. The twins, Mark and Scott Kelly. Scott is now 5 milliseconds younger than his identical twin because of spaceflight. Today, we're revealing why time isn't what you think it is and how space travel is actual time travel. If you're ready to have your mind blown, smash that like button, hit subscribe, ring the notification bell, and drop a comment below with your craziest time theory. Because this will change everything you thought you knew about time itself. Chapter 1. The Astronaut Who Came Back Younger. Let me take you back to March 14th, 2019. It was a crisp morning at the Baikonur Cosmodrome in Kazakhstan when astronaut Christina Koch, then a 40-year-old electrical engineer from North Carolina, made her final preparations before embarking on what would become the longest single space flight by a woman in history. Koch would often spend her evenings before missions stargazing, contemplating the vast mysteries of the universe that she was about to experience firsthand. It was this insatiable curiosity about the cosmos that had driven her to become an astronaut in the first place. Little did she know that her upcoming 328-day journey aboard the International Space Station would provide the most dramatic real-world demonstration of one of Einstein's most revolutionary theories. As Koch's Soyuz spacecraft lifted off from Earth, accelerating to over 17,500 miles per hour to reach orbital velocity, something extraordinary began happening to time itself around her. Every second that ticked by on her mission chronometer was running infinitesimally slower than the seconds ticking by on Earth below. This wasn't a malfunction of her equipment or some quirk of space travel. It was the universe operating exactly as Albert Einstein had predicted over a century earlier. During her record-breaking mission, Koch would often float in the station's cupola, that magnificent seven-windowed observatory that offers a panoramic view of Earth spinning beneath. As she watched our blue planet rotate through day and night cycles every 90 minutes, she was unknowingly experiencing time dilation, the stretching of time itself due to her incredible velocity and her position in a slightly weaker gravitational field than those of us stuck on Earth's surface. Think about this for a moment. While Koch was conducting experiments, exercising on the station's treadmill, and communicating with mission control, her biological processes, her heartbeat, her cellular metabolism, even the firing of neurons in her brain, were all occurring at a subtly different rate than they would have been on Earth. Every breath she took, every thought she had, every beat of her heart was happening in a time stream that moved just slightly slower than ours. When Koch finally returned to Earth on February 6, 2020, after 328 days, 13 hours, and 58 minutes in space, scientists calculated something that would have seemed impossible to anyone living before Einstein's era. She had aged approximately 0.01 seconds less than if she had remained on Earth for the same period. To put this in perspective, While everyone on Earth experienced those 328 days in their entirety, Koch experienced 0.01 seconds less of time. She had literally traveled into the future, aging more slowly than the rest of humanity. Now, I know what you're thinking. 0.01 seconds doesn't sound like much. And you're right. It's an almost imperceptibly small amount. But here's what makes this absolutely mind-blowing. This tiny fraction of a second represents proof of one of the most radical ideas in the history of science. It proves that time, something we all experience as constant and unchanging, is actually malleable. It can stretch, contract, and flow at different rates depending on how fast you're moving and how strong the gravitational field you're in happens to be. Koch's experience wasn't unique. Every astronaut who has ever traveled to space has experienced this phenomenon. Russian cosmonaut Gennady Padalka, who holds the record for the most cumulative time spent in space at 879 days, has traveled approximately 0.02 seconds into the future relative to the rest of us. The crew of Apollo 11, during their historic journey to the moon, experienced time dilation effects, albeit much smaller ones due to their shorter journey time. But here's where things get even more fascinating. Koch's time dilation wasn't just due to her incredible speed. Though traveling at 17,500 miles per hour certainly contributed to it. It was also due to her position in space, where Earth's gravitational field is slightly weaker than it is at sea level. You see, Einstein discovered that gravity itself affects the passage of time. The stronger the gravitational field you're in, the slower time moves relative to areas with weaker gravity. This means that time was pulling Koch in two different directions, so to speak. Her high velocity was causing time to slow down due to what Einstein called special relativity. But her position in a weaker gravitational field was causing time to speed up slightly due to what he called general relativity. The net effect was that the velocity-induced time dilation was stronger, resulting in her overall aging more slowly than people on Earth. This revelation blew scientists' minds when Einstein first proposed it in 1905 and 1915, and it continues to challenge our everyday understanding of reality today. We intuitively think of time as this universal constant, a cosmic metronome that ticks away at the same rate everywhere in the universe. We imagine that if you and I synchronize our watches right now, they should stay synchronized forever, regardless of where we go or how fast we travel. Einstein shattered this intuition completely. He showed us that time is not a universal constant, but rather a local phenomenon that depends entirely on your frame of reference. The faster you move through space, the slower you move through time. The stronger the gravitational field you're in, the slower time passes relative to weaker gravitational fields. Koch had experienced firsthand that time is not the rigid, unchanging dimension we perceive it to be in our everyday lives. Instead, it's more like a river, sometimes flowing faster, sometimes slower, depending on the cosmic terrain it's flowing through. When she looked down at Earth from the International Space Station, she was literally looking at a world where time was flowing at a slightly different rate than her own. This isn't just theoretical physics confined to textbooks and research papers. Time dilation has real, measurable effects that we deal with in our modern technological world. The GPS satellites orbiting Earth experience the same time dilation effects as Koch did. And if we didn't account for these effects, your GPS navigation would be off by several miles after just one day. The atomic clocks on those satellites run faster than identical clocks on Earth's surface because they're in a weaker gravitational field, but they also run slower because they're moving at high orbital speeds. Engineers have to carefully calibrate these systems to account for Einstein's predictions. As Koch floated in the space station, conducting experiments and pushing the boundaries of human endurance in the microgravity environment, she was also conducting the most profound experiment of all. She was proving that our universe operates according to principles that challenge everything our everyday experience tells us about the nature of time and space. The implications of Koch's experience extend far beyond just space travel. They force us to reconsider fundamental questions about the nature of reality itself. If time can slow down and speed up, if it's not the universal constant we thought it was, then what else about our understanding of the universe might need to be reconsidered? Koch's journey represents more than just a record-breaking space mission. It represents humanity's ongoing quest to understand the deepest mysteries of existence. Every second she spent in space, aging infinitesimally slower than the rest of us, was a second spent proving that the universe is far stranger and more wonderful than we could have ever imagined. And this is just the beginning. As we prepare to send humans to Mars and beyond, as we develop faster spacecraft and venture into regions of space with different gravitational fields, these time dilation effects will become even more pronounced. Future Mars colonists might age differently than people on Earth. Astronauts on interstellar journeys could return to find that centuries have passed on their home planet, while only years have passed for them. Christina Koch's 0.01 seconds might seem small, but they represent something monumental. They represent proof that Einstein was right, that time is not what it seems, and that the universe holds secrets that are more extraordinary than we ever dared to dream. Chapter 2: The Great Time War, Newton versus Einstein. Picture this. You're standing in the hallway of the most prestigious physics conference in history, and you overhear what might be the greatest scientific argument of all time. On one side, you have Sir Isaac Newton, the man who gave us the laws of motion and universal gravitation, confidently declaring that time is absolute and unchanging throughout the entire universe. On the other side, a wild-haired patent clerk named Albert Einstein is making the audacious claim that time itself can stretch, bend, and even slow down. This wasn't just a friendly academic debate. This was a battle for the very soul of physics itself. Einstein's revolutionary work was heavily influenced by two towering giants whose ideas seemed to be locked in an impossible contradiction. First, there were Newton's laws of motion, which had successfully explained everything from falling apples to planetary orbits for over 2 centuries. Newton's framework insisted that time moved unflinchingly forward at the same rate everywhere in the universe, a cosmic metronome that never missed a beat. According to Newton, if you synchronize 2 clocks at the beginning of time, they would remain perfectly synchronized forever, no matter where you took them or how fast you moved them through space. Second, there were the revolutionary laws of electromagnetism, laid down by James Clerk Maxwell in the 1860s. Maxwell had discovered something that would shake the very foundations of physics. Electromagnetic waves, including light, always traveled at exactly 299,792,458 meters per second in a vacuum, regardless of who was observing them or how fast they were moving. This was radically different from everything else in the universe, where velocities always depended on your perspective. Think about it this way. If you're standing on a train platform and a train passes by at 60 miles per hour, that's the train's speed relative to you. But if you're in a car, driving alongside the train at 30 miles per hour in the same direction, the train appears to be moving only 30 miles per hour relative to you. If you're driving toward the train at 30 miles per hour, it appears to be approaching you at 90 miles per hour. This is basic common sense. Velocities add and subtract depending on your frame of reference. But Maxwell's equations suggested something absolutely bizarre. Light doesn't follow these rules at all. Whether you're standing still, running toward a flashlight, or speeding away from it in the fastest rocket ever built, you would always measure the speed of light to be exactly the same, roughly 186,000 miles per second. This seemed to violate everything we knew about how motion works in the universe. Newton's notion of absolute time seemed completely incompatible with Maxwell's notion of constant light speed. If Newton's laws were truly universal, applying to everything in the cosmos without exception, then why should the speed of light be so stubbornly special? Why wouldn't light speed change depending on your perspective, just like every other velocity in the universe? This presented Einstein with a daunting dilemma that would either destroy his career or revolutionize our understanding of reality forever. Now, here's where Einstein's genius truly shines. Instead of dismissing either Newton or Maxwell, he decided to take both seriously and find a way to make them work together. But doing so would require him to challenge one of the most fundamental assumptions about reality that humans had ever made: the assumption that time flows the same way for everyone, everywhere, always. This conflict between Newton's relative velocities and Maxwell's absolute light speed can be demonstrated with one of Einstein's most brilliant thought experiments. Picture yourself standing on a train platform on a dark, stormy night. Lightning strikes simultaneously on both sides of you. One bolt to your left, another to your right. Since you're standing exactly halfway between the two strikes, the light from both bolts reaches your eyes at exactly the same moment. From your perspective, the lightning strikes were perfectly simultaneous. Now, here's where things get mind-bending. Imagine your friend is on a train that's speeding past you at an incredible velocity, let's say half the speed of light, roughly 93,000 miles per second. As the train passes by, those same two lightning bolts strike at the exact same moment they did before. But here's the crucial question. What does your friend on the speeding train observe? If light behaved like everything else in the universe, following Newton's rules of relative motion, then your friend would see the lightning strikes at different times. The light from the strike in front of the train would be moving toward him faster than normal, while the light from the strike behind the train would be moving toward him slower than normal. This means the front lightning bolt would reach him first, making it appear that the strikes weren't simultaneous at all. But remember Maxwell's discovery. Light always travels at the same speed, regardless of the observer's motion. This creates an impossible paradox. Your friend on the train measures the same speed of light coming from both directions, yet he still receives the light from the two strikes at different times. How can this be? Einstein realized there was only one possible solution to this paradox, and it was so radical that it would fundamentally change how we think about the universe itself. If the speed of light must remain constant for all observers, and if your friend on the train receives the light from the two strikes at different times, then there's only one logical conclusion. The lightning strikes didn't actually happen at the same time from your friend's perspective. Let me repeat that, because it's absolutely crucial. Events that are simultaneous for you are not simultaneous for someone moving at high speed relative to you. This isn't just about what people observe or measure. This is about the fundamental nature of time itself. Time doesn't flow the same way for everyone. Your now is not the same as your friend's now when you're moving at different velocities. But Einstein didn't stop there. He pushed this logic even further and arrived at an even more shocking conclusion. If simultaneity is relative, if different observers can disagree about when events happen, then time itself must be relative. The duration between events, the rate at which time passes, even the order in which things happen, can all depend on how fast you're moving and where you are in space. Einstein had to make a revolutionary choice. Either Newton's laws were incomplete, or the speed of light wasn't truly constant for all observers. The experimental evidence for Maxwell's equations was overwhelming. Light really did travel at the same speed for everyone who measured it. So Einstein chose to modify Newton's framework instead. To resolve the discrepancy between what you and your friend observe on the train platform, Einstein suggested something that sounded like pure science fiction. Time itself for your friend on the speeding train must be running slower relative to your time. Not slower in the sense that clocks are malfunctioning or that biological processes are being affected by some external force, but slower in the sense that time itself, the fundamental dimension in which all events unfold, is literally stretched out. Einstein called this mind-bending phenomenon time dilation, and he incorporated it into his revolutionary new theory of special relativity. The word special referred to the fact that it dealt with objects moving at constant velocities relative to each other, as opposed to accelerating objects. This was more than just a mathematical correction to Newton's laws. It was a complete reimagining of the nature of reality itself. Newton had believed that time moved forward at the same rate throughout the entire universe, like a cosmic river flowing at a steady pace. Einstein revealed that time was more like a vast ocean, with currents that flow at different speeds depending on where you are and how fast you're moving. The implications were staggering. If you could somehow travel close to the speed of light, time would slow down so dramatically that you could journey to distant stars and return to find that centuries had passed on Earth, while only years had passed for you. You would literally become a time traveler, moving through time at a different rate than everyone else in the universe. But Einstein's radical ideas didn't stop with special relativity. He soon realized that acceleration and gravity also affect the passage of time, leading to his even more revolutionary theory of general relativity. According to this theory, massive objects like stars and planets don't just exist in space. They actually warp and curve the fabric of space-time itself. Newton believed that gravitational attraction was a mysterious force that somehow reached across empty space to pull objects together. Einstein revealed that gravity isn't really a force at all. It's the curvature of space-time caused by mass and energy. Objects fall toward Earth not because they're being pulled by some invisible force, but because Earth's mass curves space-time in such a way that the shortest path through that curved space leads toward Earth's center. And here's the truly mind-blowing part. Because gravity is really curved space-time, and because time is part of that fabric, gravity affects the passage of time itself. The stronger the gravitational field, the slower time moves relative to weaker gravitational fields. This means that time runs slightly slower at sea level than it does on a mountaintop, simply because sea level is deeper in Earth's gravitational well. Einstein's theories suggested that the universe was far stranger and more interconnected than anyone had ever imagined. Space and time weren't separate, independent dimensions. They were woven together into a single four-dimensional fabric called space-time. Matter and energy weren't just things that existed in space and time. They were things that actively shaped and curved the very fabric of reality itself. The conflict between Newton's absolute time and Maxwell's constant light speed had led Einstein to one of the most profound insights in the history of science. Time is not what it seems. It's not a universal constant ticking away at the same rate everywhere. It's a malleable dimension that stretches and contracts, speeds up and slows down, depending on motion and gravity. This revelation would change everything, from our understanding of the cosmos to the technology we use every day. GPS satellites, particle accelerators, nuclear power plants, and even the simple act of looking up at the stars all depend on Einstein's insights about the true nature of time and space. But perhaps most remarkably, Einstein arrived at these revolutionary ideas not through expensive experiments or complex observations, but through pure thought. By taking the known laws of physics seriously and following them to their logical conclusions, no matter how strange or counterintuitive those conclusions might be. The great time war between Newton and Einstein wasn't really a war at all. It was an evolution, a deepening of our understanding of reality that revealed the universe to be far more wonderful and mysterious than we had ever dared to imagine. Chapter 3. The Space Station, Paradox. When time becomes your enemy. Imagine you're standing in mission control at NASA's Johnson Space Center in Houston. The year is 2025, and you're about to witness something that would have been considered impossible just a century ago. On the massive screens in front of you, two identical atomic clocks are displayed side by side. One sits securely on your desk in Houston, ticking away with precision that would make a Swiss watchmaker weep with envy. The other is floating 250 miles above your head aboard the International Space Station, carried there by an astronaut who happens to be your identical twin. Both clocks were synchronized to the nanosecond before launch. Both use the same cesium atoms vibrating at exactly 9,192,631,770 cycles per second to measure time. Both were built in the same factory, calibrated by the same technicians, and tested under identical conditions. By every measure of logic and common sense, these clocks should remain perfectly synchronized forever. After all, a second is a second, right? Wrong. Dead wrong. This scenario represents one of Einstein's most brilliant thought experiments brought to life, and it reveals a truth about our universe so counterintuitive that it challenges everything we think we know about the nature of time itself. What you're about to discover is that those two identical clocks, despite being perfect twins, will begin to diverge from the moment the space station achieves orbital velocity. The clock in space will start running differently than the one on Earth, and this difference will grow larger with each passing day. But here's the truly mind-bending part. Which clock runs faster depends on which force dominates, gravity or velocity. And the answer might surprise you. Let's dive deeper into this cosmic paradox. Your twin brother, aboard the International Space Station, is living in what physicists call a different reference frame. He's moving at an absolutely staggering 17,500 miles per hour relative to you on Earth's surface. To put this speed in perspective, he could fly from New York to Los Angeles in just 10 minutes. He's moving so fast that he orbits our entire planet every 90 minutes, experiencing 16 sunrises and sunsets every single day. Now, according to Einstein's special theory of relativity, time dilation occurs whenever objects move at high speeds relative to each other. The faster you move through space, the slower you move through time. This means that from your perspective on Earth, watching your twin brother through the mission control monitors, his clock should be running slower than yours. His heartbeat should be slower. His thoughts should be processing more slowly. Even his aging should be happening more gradually. But wait, there's a plot twist that makes this story even more fascinating. Your twin brother isn't just moving fast. He's also living in a weaker gravitational field. At the altitude of the International Space Station, Earth's gravity is about 10% weaker than it is down here at sea level. And Einstein's general theory of relativity tells us that gravity affects time too. The stronger the gravitational field, the slower time passes. This means that because your twin is experiencing weaker gravity, his clock should actually be running faster than yours. So now we have two opposing forces battling it out in a cosmic tug-of-war over time itself. The velocity effect wants to slow down your twin's clock, while the gravitational effect wants to speed it up. Which one wins? The answer lies in the precise mathematics of Einstein's equations. But let me paint you a picture of what's actually happening. Imagine time as a flowing river. On Earth's surface, you're standing in the main current, where the water flows at a steady, familiar pace. Your twin brother, however, is simultaneously experiencing two different currents. The velocity current is trying to slow down his time stream, like wading upstream against a strong flow. But the gravitational current is trying to speed up his time stream, like being caught in a downstream rapids. The net effect? The velocity wins, but just barely. Your twin brother's atomic clock, despite being in a weaker gravitational field that wants to make it run fast, is still running slightly slower than yours, because the time dilation from his incredible speed is stronger than the time dilation from the reduced gravity. After 24 hours in orbit, his clock will be behind yours by about 38 microseconds. That's 38 millionths of a second, an almost impossibly small amount, but measurable with modern atomic clock precision. But here's where the story gets really wild. Let's say your twin brother isn't just on a routine mission to the International Space Station. Let's imagine he's embarking on humanity's first mission to Proxima Centauri, our nearest star beyond the Sun, located 4.37 light-years away. To make this journey in a reasonable time frame, his spacecraft would need to reach speeds approaching a significant fraction of the speed of light. Let's say 50% of light speed, or about 93,000 miles per second. At these incredible velocities, the time dilation effects become dramatic beyond comprehension. While your twin brother travels to Proxima Centauri and back, a journey that might take him 10 years from his perspective, you would experience approximately 17 years passing on Earth. Your twin would return to find that you've aged 7 years more than he has. He might come back to discover that his children, who were toddlers when he left, are now teenagers who barely remember him. This isn't science fiction. This is the mathematical reality of Einstein's universe. Time is not the universal constant our brains evolved to perceive it as. Instead, it's more like a river with different currents, eddies, and flows, depending on where you are and how fast you're moving. But the space station paradox reveals something even more profound about the nature of reality. Let's return to your twin brother floating in the International Space Station, looking down at Earth through the cupola windows. From his perspective, he's not moving at all. He's simply floating peacefully in space, while Earth rotates beneath him. In his reference frame, you're the one who's moving. You're spinning around with the Earth at over 1,000 miles per hour at the equator, plus orbiting the Sun at 67,000 miles per hour, plus moving with our entire solar system around the galaxy at 514,000 miles per hour. So from his perspective, why shouldn't your clock be the one running slower? This is the heart of the relativity paradox. Each observer believes the other is moving, so each should observe the other's clock running slow. It seems like a contradiction that would tear apart the very fabric of Einstein's theory. But Einstein was too clever to let such an obvious problem slip by. The resolution lies in the fact that your twin brother's journey is not symmetric. While he may feel like he's at rest in his space station, he had to accelerate to reach orbital velocity, and he'll have to decelerate when he returns to Earth. During those periods of acceleration and deceleration, he experiences forces that break the symmetry of the situation. He feels pressed into his seat during launch, and he'll feel the pull of deceleration during re-entry. These accelerations create a fundamental difference between his experience and yours. You, sitting in mission control, never experience these accelerations relative to Earth. You remain in what physicists call an inertial reference frame, a fancy way of saying you're not accelerating. Your twin brother, despite floating weightlessly in orbit, is actually in a constant state of acceleration. He's falling toward Earth continuously, but his incredible forward velocity keeps him missing our planet, creating the circular orbit we call weightlessness. This asymmetry is what resolves the paradox. When all the accelerations are accounted for, when the complex dance between velocity and gravity is calculated precisely, the result is unambiguous. Your twin brother aboard the space station ages more slowly than you do on Earth's surface, by exactly the amount Einstein's equations predict. The space station paradox isn't just an abstract thought experiment. It's a reality that every astronaut lives with. Scott Kelly, who spent nearly a year aboard the International Space Station, returned to Earth having aged about 8.6 milliseconds less than he would have if he'd stayed on the ground. His identical twin brother Mark, also an astronaut, but one who remained on Earth during Scott's mission, provided the perfect control subject for this real-world demonstration of Einstein's predictions. What makes this even more remarkable is that these effects are happening all around us, all the time, in ways we never notice. The GPS satellites that help you navigate to your destination are constantly experiencing time dilation effects. If engineers didn't account for Einstein's predictions and continuously adjust the satellite clocks, your GPS would be off by several miles within hours. Every airplane flight, every high-speed train ride, even driving your car down the highway, creates tiny time dilation effects. You age microseconds less on a cross-country flight than you would sitting at home. The faster you move, the more you travel into the future relative to stationary observers. The space station paradox forces us to confront a profound truth. Time is not what it seems. Our everyday experience tells us that time flows uniformly, that simultaneity is absolute, that the order of events is the same for everyone. Einstein showed us that all of these intuitions are wrong. Time is malleable, personal, and dependent on your motion and position in the universe's gravitational fields. When your twin brother floats in the International Space Station, watching Earth turn beneath him, he's not just conducting scientific experiments or pushing the boundaries of human endurance. He's living proof that the universe operates according to principles that challenge our most fundamental assumptions about reality. Every second of his mission is a victory for human curiosity and a testament to our species' incredible ability to discover truths that seem impossible but are absolutely real. The clocks may show different times, but they're both correct. Time itself has become the ultimate paradox, relative, personal, and more mysterious than we ever imagined. Chapter 4. The Resolution. Einstein's Breakthrough. Picture this. It's 1905, and Albert Einstein is sitting in his cramped patent office in Bern, Switzerland, surrounded by towers of paperwork for mechanical inventions that would be forgotten by history. But Einstein's mind wasn't on steam engines or electrical gadgets. His mind was wrestling with a problem that was driving him to the edge of madness. A problem that would either destroy everything physicists thought they knew about the universe or reveal the most profound secret of existence itself. For months, Einstein had been tormented by an impossible contradiction. On one side stood Isaac Newton's ironclad laws of motion, which had explained the movement of planets and cannonballs for over 2 centuries. These laws insisted that all motion was relative, that there was no such thing as absolute speed. Only speed relative to something else. If you're sitting in a train, moving at 60 miles per hour, and you throw a ball forward at 20 miles per hour, someone standing on the platform would see that ball moving at 80 miles per hour. Simple addition. Universal truth. But on the other side stood James Clerk Maxwell's equations for electromagnetism, which revealed something deeply disturbing about light. No matter who measured it, no matter how fast they were moving, light always traveled at exactly 186,282 miles per second. Always. It didn't matter if you were running toward a flashlight or away from it, the light would reach you at the same speed. This flew in the face of everything Newton had taught us about relative motion. Einstein had to make a choice that would either mark him as a revolutionary genius or a complete lunatic. Either Newton's laws were incomplete, or Maxwell's speed of light wasn't truly universal. The scientific establishment had bet everything on Newton. Einstein was about to bet against the house. But here's where Einstein's true genius revealed itself. Instead of choosing one theory over the other, he asked a question that no one else had dared to ask. What if both theories were correct, but we were wrong about something even more fundamental? What if the problem wasn't with motion or light, but with time itself? Imagine Einstein in that moment, staring out his office window at the Bern clock tower, when the revelation hit him like a lightning bolt. What if time wasn't the universal, unchanging constant that everyone assumed it to be? What if time could stretch and compress like a rubber band? What if the reason light always appeared to travel at the same speed was because time itself was adjusting to make it so? This was heresy of the highest order. Since the dawn of human consciousness, time had been the one absolute truth we could count on. Kingdoms could fall, mountains could crumble, but time marched forward at its steady, unwavering pace. 1 second was always 1 second. Whether you were a peasant in a field or a king in a palace, time was democracy's ultimate expression. It treated everyone exactly the same. Einstein was about to shatter that comforting illusion forever. Let me walk you through the moment when Einstein solved the greatest puzzle in physics. He imagined two observers. Let's call them Alice and Bob. Alice is standing on a train platform, and Bob is on a train racing past her at incredible speed. Now, Alice sees two lightning bolts strike simultaneously, one at the front of the train, one at the back. Because Alice is standing exactly in the middle between the two strikes, the light from both lightning bolts reaches her at the exact same moment. To Alice, the strikes were perfectly synchronized. But what does Bob see from his speeding train? According to Newton's laws, Bob should see the lightning strikes at different times because he's racing toward one strike and away from the other. The light should reach him faster from the front strike and slower from the rear strike. But Maxwell's equations insisted that light travels at the same speed regardless of Bob's motion. So how could both things be true? Einstein's breakthrough was breathtaking in its simplicity and terrifying in its implications. He realized that for both Alice and Bob to measure light traveling at the same speed, despite their different motions, time itself had to be running at different rates for each of them. Bob's clocks had to be ticking slower than Alice's clocks to compensate for his motion through space. This wasn't just a mathematical trick or a measurement error. Einstein was claiming that time was actually, physically, running slower for Bob than for Alice. If Bob had a stopwatch and Alice had an identical stopwatch, and they both started them at the same moment, Bob's stopwatch would fall behind Alice's stopwatch. Not because there was anything wrong with the stopwatches, but because time itself was passing more slowly for Bob. But Einstein didn't stop there. His mind, now unleashed from the constraints of conventional thinking, pushed the idea even further. If motion could slow down time, what about gravity? Einstein spent the next 10 years developing what would become his theory of general relativity. And what he discovered was even more mind-bending than his original insight. Einstein realized that gravity wasn't a force pulling objects together, as Newton had believed. Instead, massive objects like planets and stars were actually warping the fabric of space and time itself. Imagine a bowling ball placed on a stretched rubber sheet. It creates a depression that causes marbles placed nearby to roll toward it. Similarly, Earth creates a depression in the fabric of space-time that causes objects to fall toward it. But here's the kicker. Time runs slower in regions of stronger gravity. The closer you are to a massive object, the more space-time is warped, and the slower time passes relative to regions with weaker gravity. This meant that time wasn't just affected by motion, it was also affected by gravity. To get rid of the discrepancy between Newton's and Maxwell's theories, Einstein had discovered that time itself was malleable, stretching and contracting based on both velocity and gravitational fields. He called this mind-bending phenomenon time dilation, and his newfound theories special relativity and general relativity. But Einstein's theories weren't just philosophical musings. They made specific, testable predictions. If he was right, then clocks at the top of a mountain should run faster than identical clocks at sea level, because they're in a slightly weaker gravitational field. If he was right, then objects moving at high speeds should experience time more slowly than stationary objects. The scientific community was skeptical, to put it mildly. How could time, the most fundamental aspect of existence, be relative? How could something as abstract as motion or gravity actually change the rate at which time passes? It seemed absurd, impossible, a violation of common sense. But Einstein had done something that would cement his place in history forever. He had taken two apparently contradictory theories and revealed that they were actually two pieces of a much larger, more beautiful puzzle. Newton's laws were correct within their domain, and Maxwell's equations were correct within theirs. But both were operating within a universe where time and space were far more flexible and interconnected than anyone had ever imagined. Einstein called this unified framework space-time, a four-dimensional fabric where space and time were woven together into a single entity. In this framework, what we perceive as separate dimensions of length, width, height, and time were actually different aspects of one seamless reality. The implications were staggering. If Einstein was right, then the universe was fundamentally different from everything humans had ever believed. Time wasn't universal. It was personal. Your time could run differently from my time. The past, present, and future weren't fixed points, but fluid concepts that depended on your frame of reference. But perhaps most incredibly, Einstein's theory suggested that time travel might actually be possible, not in the Hollywood sense of stepping into a machine and traveling to specific dates, but in the sense that different observers could legitimately experience time at different rates. Someone moving at high speed or in a strong gravitational field could literally age more slowly than someone else, effectively traveling into the future. As Einstein finalized his equations in that little patent office in Bern, he couldn't have imagined that one day his theories would be tested by astronauts orbiting Earth at 17,500 miles per hour. He couldn't have foreseen that GPS satellites would need to account for his predictions to work properly. He couldn't have imagined that particle accelerators would routinely observe subatomic particles experiencing time dilation exactly as his equations predicted. But in that moment of revelation, when Einstein realized that time itself could bend and stretch and flow at different rates, he had unlocked one of the universe's deepest secrets. He had discovered that reality was far stranger, far more flexible, and far more wonderful than anyone had ever dared to imagine. Einstein's choice to trust in the mathematics rather than in common sense had led him to perhaps the most counterintuitive truth in all of science. Time, the one thing we thought we could count on to be constant and universal, was actually the most variable thing in the universe. And with that realization, Einstein didn't just solve the conflict between Newton and Maxwell. He revolutionized our understanding of existence itself. Chapter 5. When Space and Time Became One. The birth of space-time. Picture this. It's 1905, and the scientific world is about to be turned completely upside down. For over 2 centuries, humanity had lived comfortably with Isaac Newton's vision of the universe, a cosmic clockwork where space was an empty stage and time was the universal conductor, keeping perfect rhythm everywhere from Earth to the farthest star. Space was space, time was time, and never the two shall meet. But Albert Einstein, that wild-haired patent clerk in Switzerland, was about to shatter this comfortable reality with an idea so radical that even today, over a century later, it still makes our brains hurt. Newton believed that space and time moved independently and uniformly throughout the universe, like 2 separate rivers flowing in parallel, never touching, never influencing each other. In Newton's universe, if you synchronized 2 clocks, one on Earth and one on Mars, they would tick away in perfect harmony for eternity. Time was absolute, unchanging, and universal. It didn't matter if you were sitting in your living room or hurtling through space at incredible speeds. Time marched on at exactly the same pace everywhere. But Einstein had just made a discovery that would change everything. Through his revolutionary theories of special and general relativity, he had realized something that defied all common sense. Space and time weren't separate entities at all. They were intimately connected, like dance partners locked in an eternal waltz. When one moved, the other had to follow. When one stretched, the other contracted. They were, in Einstein's mind-bending revelation, 2 aspects of the same fundamental reality. Einstein had discovered that space and time stretch and contract together, varying with velocity and gravity in ways that would have seemed like pure fantasy to anyone living in Newton's era. Due to their incredible malleability, their ability to bend, twist, and flow like cosmic putty, time and space deserved to be considered as one unified entity. In fact, Einstein claimed that the two were literally one and the same, forever intertwined in what he called the fabric of reality itself. Together, these once separate concepts formed a four-dimensional tapestry that Einstein named spacetime, a cosmic stage upon which all the grand events of the universe would unfold. But this wasn't just some abstract mathematical concept buried in dusty physics textbooks. This was the actual structure of reality, and it was about to revolutionize how we understood everything from falling apples to the orbits of planets, to the aging of astronauts floating hundreds of miles above our heads. To understand just how radical this idea was, imagine you're watching your favorite movie. In Newton's world, the movie screen would be space, a flat, unchanging backdrop, and time would be the film projector, running at a constant speed, projecting each frame at exactly the same rate. The screen never changes, the projector never varies its speed, and the movie plays out predictably from beginning to end. But Einstein's universe is more like a funhouse mirror version of that movie theater. The screen itself can stretch and compress, warp and bend. The projector can speed up or slow down, depending on how the screen is moving and how much mass is sitting on it. Sometimes the screen might be stretching so much that what should be a 1-hour movie takes 2 hours to play. Other times, it might compress so much that the same movie finishes in just 30 minutes. The screen and the projector are no longer separate. They're part of the same system, each affecting the other in ways that would have been unimaginable in Newton's rigid theater. This wasn't just theoretical speculation. Einstein's radical new understanding of space-time made predictions that could be tested, measured, and verified. And when scientists did test them, they discovered that Einstein was absolutely right. Space and time really were connected in the most fundamental way possible. Consider what happens when you're driving down the highway at 60 miles per hour. In Newton's world, you're simply moving through space while time ticks along at its usual pace. But in Einstein's world, something far more profound is occurring. As you speed up, you're actually moving through space-time itself, and this motion has consequences. The faster you move through the space part of space-time, the slower you move through the time part. It's as if the universe has a cosmic speed limit, and the total amount of motion you can have through space-time is fixed. Speed up through space, and you must slow down through time. This is why astronauts like Christina Koch age more slowly in space. By traveling at 17,500 miles per hour around Earth, she was moving rapidly through the space dimension of space-time, which meant she had to move more slowly through the time dimension. The faster she moved through space, the slower she moved through time. Not because of some mysterious force acting on her clocks or her biology, but because space and time are fundamentally connected aspects of the same reality. But Einstein's revelation went even deeper. He discovered that massive objects like stars and planets don't just sit passively in space. They actually warp and curve the fabric of space-time around them. Imagine stretching out a large rubber sheet and then placing a bowling ball in the center. The weight of the ball creates a depression, a curved well in the sheet. Now, if you roll a marble across the sheet, it won't travel in a straight line anymore. Instead, it will curve around the depression created by the bowling ball, following the warped geometry of the sheet itself. This is exactly what happens in our universe, except instead of a rubber sheet, we have the four-dimensional fabric of space-time. And instead of bowling balls and marbles, we have stars, planets, and everything else in the cosmos. The sun doesn't pull Earth toward it with some mysterious gravitational force. Instead, the sun's enormous mass curves space-time around it, and Earth simply follows the natural geometry of this curved space-time, like a marble rolling around the depression in our rubber sheet analogy. This curvature of space-time explains not just the orbits of planets, but also why time runs differently in different gravitational fields. The deeper you go into a gravitational well, the closer you get to a massive object like Earth, the more curved space-time becomes, and the slower time flows relative to regions where space-time is less curved. This is why time moves slightly faster for astronauts on the International Space Station compared to people on Earth's surface, at least due to the gravitational component of time dilation. The space station orbits in a region where Earth's gravitational field is weaker, where space-time is less curved than it is down here on the surface. In this less curved region of space-time, time flows slightly faster than it does in the more curved space-time near Earth's surface. But here's where it gets truly mind-bending. Einstein realized that what we call gravity isn't really a force at all. It's geometry. When you drop a ball and it falls to the ground, it's not being pulled by some mysterious gravitational force. Instead, it's following the straightest possible path through curved spacetime, what mathematicians call a geodesic. The ball thinks it's traveling in a straight line, but because spacetime itself is curved by Earth's mass, that straight line appears curved to us. This geometric understanding of gravity explained mysteries that had puzzled scientists for centuries. Why do all objects fall at the same rate in a gravitational field, regardless of their mass? Because they're all following the same curved geometry of spacetime. Why does light bend when it passes near massive objects? Because even massless particles like photons must follow the curves in spacetime created by gravitational fields. The implications of Einstein's space-time revolution extend far beyond just explaining the motion of planets and the behavior of clocks. This unified understanding of space and time as a single, malleable fabric opened up possibilities that would have been pure science fiction in Newton's era. If space-time can be curved by mass and energy, then perhaps it can be manipulated in other ways. Maybe space-time itself can ripple and wave, carrying information across the cosmos. Maybe there are shortcuts through space-time, wormholes that could connect distant regions of the universe. These aren't just fantasies anymore. We've detected gravitational waves, ripples in space-time itself, caused by colliding black holes billions of light-years away. We've measured the precise curvature of space-time around our own sun. We've seen how massive galaxy clusters act like cosmic lenses, bending light from distant galaxies and revealing the hidden architecture of space-time on the largest scales imaginable. For astronauts like Christina Koch, Einstein's unified spacetime isn't just an abstract concept. It's their daily reality. Every moment they spend in orbit, they're experiencing the malleability of spacetime firsthand. Their slightly slower aging isn't just a curiosity. It's direct evidence that space and time really are woven together into a single, dynamic fabric that responds to motion and mass in ways that our everyday experience could never prepare us for. When Koch looked down at Earth from her perch on the International Space Station, she wasn't just seeing our planet from a different spatial perspective. She was seeing it from a different temporal perspective as well. She was literally looking at a world where time was flowing at a slightly different rate than her own, where the curved space-time created by Earth's mass was creating a temporal landscape as varied and complex as any mountain range or ocean. Einstein's revelation that space and time are one hasn't just changed physics. It's changed our entire understanding of what it means to exist in this universe. We're not just moving through space as time ticks by. We're surfing through space-time itself, riding the curves and waves of this four-dimensional cosmic ocean. Every step we take, every breath we breathe, every heartbeat we experience is happening within this dynamic, ever-changing fabric of reality that Einstein first glimpsed over a century ago. And the most beautiful part? This isn't the end of the story. It's just the beginning. As we venture deeper into space, as we build faster spacecraft and explore regions of intense gravitational fields, we'll discover even more about the strange and wonderful nature of space-time. Christina Koch's journey was just one small example of humanity learning to navigate this four-dimensional reality that Einstein revealed to us. The real adventure is just getting started. Chapter 6: The Space Station Time Machine. Picture this. You're floating 250 miles above Earth, traveling at an absolutely mind-bending 17,500 miles per hour, while the planet spins beneath you like a giant blue marble. Every 90 minutes, you witness a complete sunrise and sunset. Every breath you take, every heartbeat in your chest, every thought firing through your neurons is happening in a bubble of time that moves just slightly differently than time on the surface below. You've become, quite literally, a time traveler, and you don't even realize it. This isn't science fiction. This is the reality that every astronaut aboard the International Space Station experiences every single day. They're living proof that Einstein's most mind-bending predictions about time and gravity aren't just theoretical curiosities buried in dusty physics textbooks. They're measurable, observable phenomena that affect real human beings in real time. Let me tell you about Scott Kelly, the American astronaut who spent 340 consecutive days aboard the International Space Station from 2015 to 2016. When Kelly launched from the Baikonur Cosmodrome in Kazakhstan, he left behind his identical twin brother Mark, a retired NASA astronaut, on Earth. This wasn't just any space mission. It was the perfect natural experiment to test Einstein's theories on actual human beings. As Scott's Soyuz spacecraft roared to life and pushed him away from Earth's surface, something remarkable began happening to the fabric of space-time around him. Einstein had predicted that massive objects like Earth don't just sit passively in empty space. They actually warp and curve the invisible fabric that underlies all of reality. Think of it like this. Imagine you have a large trampoline stretched tight. If you place a bowling ball in the center, it creates a deep depression in the surface. Now, if you roll marbles near the bowling ball, they don't travel in straight lines. They curve and spiral around the depression created by the bowling ball's weight. This is exactly what Earth does to space-time. Our planet's enormous mass, all 6 trillion kilograms of it, creates a deep well in the fabric of spacetime. And here's the mind-blowing part. Time itself flows more slowly at the bottom of this gravitational well than it does at the edges. So as Scott Kelly rocketed away from Earth's surface toward the International Space Station, he was literally climbing out of Earth's gravitational time well. Up there, 250 miles above our heads, Earth's gravitational pull is about 10% weaker than it is at sea level. This might not sound like much, but it's enough to make time tick just slightly faster for Scott compared to his Earth-bound twin brother Mark. But here's where things get really interesting. And this is where Einstein's genius truly shines. Scott wasn't just escaping Earth's strongest gravitational field. He was also moving at an absolutely incredible speed. To maintain orbit around Earth, the International Space Station has to travel at 17,500 miles per hour. That's fast enough to circle the entire planet in just 90 minutes. That's fast enough to travel from New York to Los Angeles in about 10 minutes. And Einstein had predicted that this incredible velocity would have its own effect on time. It would make time slow down for Scott relative to his brother on Earth. This is the essence of Einstein's special theory of relativity. The faster you move through space, the slower you move through time. So now, Scott Kelly found himself caught between two opposing forces affecting the flow of time around him. His position in a weaker gravitational field was making time speed up slightly, while his incredible velocity was making time slow down. It was like being pulled in two different directions by invisible cosmic forces. Forces that Einstein had predicted would exist over a century earlier. During his year in space, Scott Kelly experienced something that would have been incomprehensible to anyone living before Einstein's era. Every morning when he woke up and looked out the station's cupola at Earth spinning below, he was looking at a world where time was flowing at a measurably different rate than his own. Every phone call he made to his brother Mark was a conversation between two people experiencing time differently. Every video conference with mission control on Earth was a meeting between individuals whose clocks were literally ticking at different rates. The numbers are staggering when you really think about them. During his 340 days in space, Scott Kelly aged approximately 8.6 milliseconds less than his twin brother Mark. That's 8.6 thousandths of a second, a period so brief that you couldn't even perceive it if you tried. But those 8.6 milliseconds represent something profound. They represent proof that time is not the universal, unchanging constant we experience it to be in our everyday lives. Those milliseconds prove that time is malleable, flexible, and dependent on your motion and your position in gravitational fields. They prove that Einstein was right when he said that space and time aren't separate, independent entities, but rather two aspects of a single, unified fabric that can be stretched and compressed by mass and energy. But Scott Kelly's experience goes far beyond just the physics. Think about what it means on a human level. For nearly a year, Scott was literally living in a different time stream than every other human being on Earth. His biological processes, the beating of his heart, the firing of his neurons, the replication of his DNA, were all happening in a bubble of time that moved just slightly slower than the time experienced by his family and friends below. When Scott finally returned to Earth in March 2016, after 340 days of orbiting our planet, he had experienced something that challenges our most fundamental assumptions about the nature of reality. He had lived through nearly a year in which time itself moved differently for him than it did for the rest of humanity. Those 8.6 milliseconds might seem insignificant, but they represent one of the most profound confirmations of Einstein's theories ever conducted with actual human subjects. The implications of Scott Kelly's experience extend far beyond just confirming Einstein's predictions. They give us a glimpse into the future of human space exploration. When we finally send astronauts to Mars, a journey that could take 6 to 9 months each way, these time dilation effects will become even more pronounced. Mars-bound astronauts will be traveling much faster than orbital velocity for extended periods, and they'll be venturing into regions of space where gravitational fields are different from those near Earth. Future Mars colonists might find themselves aging at measurably different rates than people on Earth. A person who spends decades living on Mars, with its weaker gravitational field, might age slightly faster than their Earth-bound relatives. Astronauts, on even more ambitious interstellar journeys, could experience time dilation effects so dramatic that they return to Earth to find that decades or even centuries have passed, while only years have passed for them. But it's not just future space travelers who are affected by these cosmic time distortions. The technology you use every day, your smartphone's GPS for example, has to account for Einstein's predictions about time dilation. The GPS satellites orbiting Earth experience the same gravitational and velocity-induced time effects as astronauts like Scott Kelly. If engineers didn't carefully calibrate these satellites to account for Einstein's theories, your GPS would be off by several miles after just 1 day of operation. Every time you use your phone to navigate to a restaurant, check your location, or get directions somewhere, you're relying on technology that works only because we understand and can compensate for the effects of time dilation. Einstein's seemingly abstract theories about the nature of time and space have become essential to the functioning of our modern technological civilization. Scott Kelly's year in space represents more than just a remarkable achievement in human endurance and scientific research. It represents a real-world demonstration that we live in a universe far stranger and more wonderful than our everyday experience suggests. It proves that time, this thing we take for granted, this invisible river we all seem to be flowing down together, is actually more like a complex landscape of rushing rapids, gentle pools, and swirling eddies. When Scott Kelly looked down at Earth from the International Space Station, watching our planet rotate through its day and night cycles, he was seeing more than just geography and weather patterns. He was seeing a world locked in a different rate of temporal flow than his own. Every city light twinkling below, every storm system swirling across the continents, every sunrise and sunset was happening in a time stream that moved just slightly faster than the one he was experiencing. Those 8.6 milliseconds that Scott gained during his year in space might be imperceptible to human senses, but they represent something monumental in the history of science and human understanding. They represent proof that Einstein's revolutionary insights about the nature of time and space aren't just elegant mathematical abstractions. They're fundamental features of the reality we live in. As we stand on the threshold of becoming a truly spacefaring civilization, with plans for permanent bases on the Moon and Mars, with dreams of interstellar travel and exploration of distant worlds, Scott Kelly's experience gives us a preview of the temporal complexities that await us among the stars. In the cosmos beyond Earth, time itself becomes a traveler's companion, sometimes moving faster, sometimes slower, always reminding us that the universe is far more extraordinary than we ever dared to imagine. Chapter 7: Your Body's Secret Time Machine. The Universal Truth About Time. Picture this. You're standing in mission control at NASA, watching two identical atomic clocks display on the massive screens in front of you. One clock is here on Earth, ticking away in perfect synchronization with every atomic process happening in your body right now. The other clock is 250 miles above your head, aboard the International Space Station, keeping time for astronauts who are hurtling through space at 17,500 miles per hour. Here's what would blow your mind if you could see it happening in real time. These two supposedly identical clocks are actually running at different rates. And this difference reveals the most profound truth about the nature of time itself. To understand how velocity and gravity affect time at the most fundamental level, let's consider the simplest timekeeping mechanism imaginable: the vibration of atoms themselves. Every atom in the universe oscillates at specific frequencies, creating natural clocks that are billions of times more precise than anything humans have ever built. A second passes each time a cesium atom completes exactly 9,192,631,770 oscillations. This is literally how we define what a second means in our modern world. Now let's imagine two people experiencing time through these atomic processes under radically different conditions. Meet Commander Sarah Mitchell, floating weightlessly aboard the International Space Station as she conducts a routine maintenance check on the station's life support systems. Meanwhile, her identical twin sister, Dr. Lisa Mitchell, stands in a physics laboratory at MIT, conducting the exact same atomic clock experiment with identical equipment. Both sisters are watching cesium atoms oscillate. Both are breathing roughly 15 times per minute. And both are completely unaware that they're participating in the most mind-bending experiment in the history of science. What do each of the two sisters observe as time flows around them? What they're experiencing is eerily similar to what happens when you watch two metronomes ticking at slightly different rates. One keeping perfect time, the other running just a fraction slower. For Sarah in space, every atomic process in her body, from the oscillation of atoms in her bones to the electrical impulses firing in her brain, is occurring in a time stream that flows like a river, moving just slightly slower than the temporal current flowing through Lisa's laboratory on Earth below. This means that Sarah's heart, beating approximately 70 times per minute, according to her onboard chronometer, is actually completing each beat in a duration that's infinitesimally longer when measured against Lisa's earthbound time frame. Sarah's neurons firing electrical signals as she marvels at the aurora dancing across Earth's atmosphere. are transmitting these impulses through biological pathways that exist in a pocket of space-time where time itself moves at a marginally different pace. The truly fascinating aspect is that neither sister feels anything unusual about her own experience of time. Sarah doesn't feel sluggish or slow. Her thoughts race at what feels like normal speed. Her reflexes respond instantly to her commands, and her perception of duration feels completely ordinary. This is because time dilation affects everything within each reference frame uniformly. Sarah's atomic clocks, her biological processes, her consciousness, and even her perception of time all slow down together in perfect harmony. It is obvious that the magnitude of this temporal difference is proportional to both Sarah's orbital velocity and the difference in gravitational field strength between her position and Lisa's. At the ISS's altitude of 250 miles and speed of 17,500 miles per hour, the mathematics of Einstein's equations predict that Sarah will age approximately 0.01 seconds less than Lisa over the course of a year-long mission. But here's where the science becomes absolutely mind-blowing. This time, dilation doesn't just affect mechanical clocks or abstract physics experiments. It affects every single biological process happening inside Sarah's body. Her digestive system breaks down nutrients according to the rhythm of space-time at her orbital altitude. Her immune system responds to potential threats with timing that's governed by the fundamental flow of time in her reference frame. Even her dreams during sleep unfold in a temporal landscape that's subtly different from the one her earthbound twin experiences. Time dilation affects every biological clock in the human body. Whether it relies on the simple vibration of atoms and cellular structures, or the complex cascade of hormonal signals that regulate circadian rhythms. Sarah's internal biological clock evolved over millions of years to synchronize with Earth's 24-hour rotation, is now beating to the rhythm of a cosmic timekeeper that operates at a slightly different tempo than the one her evolutionary ancestors were designed to follow. Consider what this means for Sarah's DNA. That twisted ladder of genetic information that makes her uniquely human. Every time her cells divide to replace aging tissue, every time her genetic machinery copies itself to create new cells, every time her body repairs damage at the molecular level, these processes are occurring according to the fundamental flow of time in her orbital environment. Sarah's genetic code is being read, transcribed, and translated in a time stream that flows at a measurably different rate than identical processes happening in Lisa's body on Earth. The implications extend even deeper into the quantum realm. The electrons orbiting atomic nuclei in Sarah's body are completing their quantum mechanical dance according to the warped space-time geometry at her altitude. The chemical bonds holding her proteins together are vibrating at frequencies determined by the gravitational and velocity effect she experiences 250 miles above Earth. Even the radioactive decay of unstable atoms in her body, processes that form the foundation of how we measure geological timescales, are occurring at rates that differ infinitesimally from identical processes happening at sea level. This is why GPS satellites, which orbit Earth at altitudes of about 12,500 miles, require constant corrections for time dilation effects. The atomic clocks aboard these satellites run fast compared to identical clocks on Earth's surface because they experience weaker gravity, but they also run slow because they're moving at high orbital speeds. Without accounting for these relativistic effects, your GPS navigation would be off by several miles after just one day of operation. And here's the part that will completely revolutionize how you think about your own existence. You are experiencing time dilation effects right now, at this very moment, simply by virtue of being a human being with height. Your head is literally older than your feet. The difference is incredibly small. We're talking about nanoseconds over a human lifetime, but it's real and measurable. Your head experiences slightly weaker gravity than your feet because it's farther from Earth's center, causing time to flow infinitesimally faster for the neurons in your brain compared to the atoms in your toes. Time dilation affects every biological system imaginable, whether it relies on basic electromagnetic forces holding your atoms together or the complex quantum mechanical processes that enable consciousness itself. In fact, even the thoughts you're having right now, as you process this information, are occurring in neural networks where time flows at subtly different rates from the top of your head to the base of your brainstem. But let's push this even further into the realm of the truly extraordinary. As humanity prepares for missions to Mars, these time dilation effects will become dramatically more pronounced. A round-trip journey to Mars, taking approximately 2 years and involving speeds much greater than current space missions, could result in astronauts returning to Earth having aged several seconds less than people who remained on the planet. Future interstellar missions, if we ever develop the technology to travel at significant fractions of light speed, could create time differences measured in years or even decades. Imagine astronauts departing for Proxima Centauri, our nearest stellar neighbor, traveling at 10% the speed of light. When they return after what feels like a 50-year round trip to them, they would find that nearly 52 years have passed on Earth. Their friends and family would have aged 2 additional years, while the space travelers remained relatively young. This isn't science fiction. This is the inevitable consequence of the fundamental structure of space-time itself. The universe has built time dilation into the very fabric of reality. Every subatomic particle that zips through cosmic ray detectors experiences dramatic time dilation, allowing unstable particles that should decay in microseconds to survive long enough to reach Earth's surface from the upper atmosphere. Every photon of light that reaches your eyes from distant stars has traveled through regions of space-time where time flows at different rates due to the gravitational influence of massive objects. As we stand on the threshold of becoming a truly spacefaring civilization, these relativistic effects will fundamentally reshape human society. Spaceborne children might age at different rates than their Earth-born siblings. Interplanetary commerce will need to account for the temporal complexities of synchronizing transactions across different gravitational environments. Love relationships will face the unprecedented challenge of partners aging at different rates depending on their chosen careers and locations in the solar system. Yes, that's right. Every single process that makes you a living, thinking, feeling human being is subject to the strange and wonderful effects of Einstein's spacetime. Your consciousness, your memories, your emotions, your very sense of self, all exist within the flowing river of time that can speed up, slow down, and bend according to how fast you're moving and how deep you are in gravity's embrace. Thank you for joining us on this incredible journey through the mysteries of time dilation here at the Sleep Lab. We hope this exploration of Einstein's most mind-bending discovery has left you with a profound new appreciation for the strange and beautiful universe we inhabit. Every moment you've spent watching this video has been a moment spent experiencing the fundamental weirdness of space-time itself. If this kind of mind-expanding science content keeps you up at night, wondering about the deeper mysteries of existence, make sure you're subscribed to the Sleep Lab and hit that notification bell, because we've got many more cosmic secrets to uncover together. Until next time, remember, you're not just living in the universe, you're living in space-time itself. And that makes you part of the most extraordinary story ever told.